Good afternoon and welcome to the second lecture on algorithms and data structures. Last week we started with the lecture, so in the beginning I will always do a quick revision of the previous week and then we'll go ahead with the next content. Today we may need again a little bit more than 90 minutes, but this will be also in your interest, so you'll be able to advance with the coursework. So if you can spend a little bit more time today on the live lecture, that would be very helpful. Last week, we started with looking into why this course is actually essential, because for somewhat sophisticated software, we need algorithms and data structures, and in order to build them, we need lots of mathematics eventually. We looked at definitions of what an algorithm is. We saw and contrasted these definitions. We saw some example algorithms that we will also discuss in this course, like quicksort, merge sort, fast matrix multiplication, and others. We saw how we can classify algorithms into various categories. We looked at deterministic and non-deterministic ones, which we also call stochastic, recursive or iterative, exact or approximate, serial, parallel, or distributed. And there are more distinctions, but these are the key ones that we will focus on in this course. We looked at what a data structure is and some examples. The goal of this course is we build not just algorithms and data structures, but the ones that can handle or that can do certain tasks efficiently. We are surrounded by sophisticated algorithms all day long, and that's something I find very exciting. In this course, we will lay the foundation for most of the things you'll be doing as a computer scientist, because you will always be dealing with algorithms and data structures, and you need to analyze how efficient they are and try to improve them. So this course is a foundation for that. We also saw that this course will be challenging, but it's definitely doable if you follow the lectures, if you do the coursework and prepare for the exams and know what this course is about. You still need this competency despite ChatGPT and other AI tools, because it's not too much about coding in this course, but rather how to design these algorithms and data structures. So it's largely a problem-solving skill, and that's what you still need to learn. And then how you turn it into code, that's a different question. But this course is not about coding, it's about concepts, yet we will implement them in order to see how they work and experiment with them. We looked into the structure of this course. There were quite a lot of students today in the lab in some of the 4 sessions. We saw also quite some students online. And we started with the coursework. And last week, we also had an intro to Python. And this is what today's coursework was about, largely the Python primer. And if you're done with the Python primer, we are unable right now to continue with the graphs in the coursework, because we first need to do some lecture. I hope we can advance with this today, so there is time for you to work next week in the lab on these problems. However, if that's not, or if you want to work already now or on the weekend or whatever on more Python or more problems, work on the mandatory problem, because the pattern matching algorithms are independent from the content of this course. So all you need is coding. And if you're okay with Python, you can start with this and you can read in the book how these pattern matching algorithms work. Then we started with graphs, which are a foundation data structure, which is very generic. And all our data structures in this course will be some kind of graph eventually. So all our algorithms will be, or almost all of them will be some kind of graph algorithm to operate on this. And we'll be looking into this. And we started with the graph definition. When we looked into the Cartesian product, we saw what a graph is, example graphs. We saw that these are undirected graphs, and we looked into the adjacency matrix. And we will continue now with a few more variations of graphs. And for this, I will switch back to my iPad. So last week we saw a graph is a tuple of vertices and edges. So V is a set of vertices, sometimes also called nodes. And we saw for our simple undirected graph, we saw that the edges is again a set, but it's a subset of a bigger set. And there were a few essential elements like this V squared. V is the set of vertices, and V squared, remember, is the Cartesian product of V with itself. And from there, we get these tuples, x, y, but a tuple is ordered. So we convert this tuple into sets, x, y, and the order between x and y doesn't matter because it's a set. And then we have this big set, which has these subsets, x, y. And because these subsets, x, y, are subsets and not tuples, there's no order. So and that's why it's an undirected graph. We have a connection between x and y, but not from x to y or from y to x. Simply, it's in both directions, so it's unordered. And we also had one constraint in which we said x and y must be different. Only those connections are possible. And with this, we actually did not allow loops. Now we want to allow loops. We can look at a sample graph, just a very simple one. We say there are 3 nodes, 1, 2, and 3. So 1 and 3 is connected, and 2 and 3, but we also have a loop in 2, which is not possible with our initial definition because we say x and y must be different, but we can just leave this out and we can say, well, we want these subsets x and y from these tuples x, y that come from v squared, and we leave out that condition in which we said that x and y must be different. And then we are actually now permitting loops. So, and step by step, we will now look at other graphs, and we will, for now, always keep it that a graph is a tuple of v and e. V is just a set of vertices. We've seen this. And we will simply look at E, and we will look at what it is a subset of. And we will make this increasingly more complex. Just for this sample graph, we could also think about an adjacency matrix as a quick practice. So this would be the adjacency matrix. We see 1 is connected to 3, and 3 is connected to 1 because it's still undirected. Last week we had a notation with these commons, 1, 2, 3, 1, 2, 3, and 1 is connected to 3, so is 3 connected to 1, and 2 is connected to 3, and 3 is connected to 2. And what do I need to do in order to add this loop? Maybe you can tell us either orally or in the chat what I still need to add in order to add this loop. Then let us know where we need to add a 1 entry. Exactly, a 2, 2. This refers to the loop. And then we have this loop, and all the other entries are 0 because there are no connections. And since it's an undirected graph, the matrix is symmetric. So symmetric means it's the same as its transpose. Now we can think about slightly different graphs. What I want now is a directed graph. So our E will look different. We want directed graphs. One directed graph could be, just an example here, say 1, 3, and 2. And 1 is connected to 2, 2 is connected to 3, and 3 is connected to 2. So we see now this is a directed graph, and we have these arrows. And this is just one example graph. And from a generic perspective, we now have to think about what E would look like and E would be a subset of a bigger set where, and I'll highlight this in red, where we now have tuples xy, and these tuples xy, they are as an element of the V squared. And again, we will add, this is an and, that x and y must be different. So this is a big difference now, because before we had these subsets, now we have subtuples in our big set. Makes a huge difference from the notation. And that's why we last week revised what are sets, what are tuples, what are Cartesian products, because all of this needs to be well defined. And we will think about now, what could our E look like for this example? So I want to know from you that you define and send us in the chat what E would look like for this example graph where we say we have directed connections. If you have a solution, send them to the chat. Concretely, it's 3 arrows, so or 3 edges. So we have 3 tuples in our set E, and I'll see if we get any good suggestions from you. So we have the connection 1 to 3, 2 to 3, and 3 to 2. So the and it's not written well. Just wait a second. I'll remove this. So now it looks better. So E is still a set, but in this set, we put tuples, not subsets anymore, because it's directed now. What we can do next is we can think about, and I can develop this step by step. I can amend this now, and I say I want directed graphs that permit loops. What do I need to amend in my definition that I have here if I say I want to permit loops? Oh, I made a mistake. I'm sorry. I saw this in the chat. You're right. There's no 1, 3. It's a 1, 2. My mistake. There were quite some comments, so it's correct. There's a 1 to 2, 2 to 3, and 3 to 2. So was my mistake. Sorry. It's a live demo, so it's not a professional video recorded, so mistakes sometimes happen, but they will get corrected on the fly. We have lots of examples in the slide deck which are curated. Now, if I want to permit loops where I want to allow something like this. I want to have a loop in 2. How would I need to amend my definition in order to make this possible? It's correct. We have to remove this. So we can also move the closing one here. So now this we have the tuple xy that is from the tuple xy, which is an element of V squared. Could this be further simplified? Because before we had written this lengthy definition because we said x and y must be different. Is there any suggestion how we could further simplify this? Because it is too long now when we have our directed graph that permits loops. If you think you see how it could be improved, maybe raise your hand or thumbs up. If you don't see it, maybe red sticker or thumbs down, something like this. So I say here that one person sent screen response, how do you think this could be simplified? Remove the first part. What do you mean by remove the first part? Maybe turn on your mic and tell us what could be removed. So one person suggests somehow remove this. Well, almost. Becomes even simpler. For directed graphs permitting loops, we could simply say that E is a subset of V squared. It's the same because in V squared we have these XY tuples and we have XY tuples that we keep from there, but we have removed any constraints we had before and we now don't need to convert to sets or something. So we say E is a subset of V squared. For our graph here, we have added one loop. So what do I need to add in its E in order to make the definition down here match to our visualization from before? Any suggestion what I need to add? We saw it in the chat. 2, 2, because I have the loop. So this looks fine. And we can also think about the adjacency matrix to represent this graph. It's an alternative representation. So 1, 2, and 3, and 1, 2, and 3. But because it's a directed graph now, I need to define if the rows or columns are the from or to, because these matrices will not be symmetric anymore. I will say now that the rows are the from and the columns are the to. But this is totally, you can also just transpose it and define it the other way around. It's just a definition if you say the rows are the from and the columns are the to, vice versa. We can say we are connected from 1 to 2, which is this green one here. So I say 1 goes to 2, so I put here, we have the loop in 2, so from 2 to 2. And I want you to quickly complete this and send your suggestion of what this whole matrix may look like to the chat, please. So there's one suggestion in the chat. So we see 2 is connected to 3. So from 2 to 3 would be a 1 here. And from 3, so you would put in these 1s and then these 0s. But ideally, you would always just put some comment there for the row and column from where to where, because if you see it the other way around, you would just have the transpose of the matrix. But just not to confuse anyone, you would just clearly define what the rows and columns mean. Then we can look at an extension of this. What we want now is we want a different type of graph, because so far the graph was always a tuple of vertices and edges. So we can introduce now something different. What I want is I want directed weighted graphs that permit loops. What I want is, I'll just put you an example there. I want a graph that looks something like this. I have node 1, I have node 2, I have node 3, and node 4. And I want these edges to be directed Nothing new. So far, we had also directed them. But I also want them to have weights. And the weight would be a value assigned to an edge. So we could say there are different weights. From 1 to 2 would be 3. From 2 to 1 would be 2. Would have a 4 here, a 1, and a 2, just as examples. So these are weighted ones, something our model so far cannot represent yet. So we'll look into it. We say a graph is now a tuple of v and e as before, but we will introduce a new function d, which is a distance function. We have our v as before, set of vertices. And we have our e as before. It's a subset of v squared because we permit loops. But we need one more element now, which is the new one. It's d. And d is something that is a function that maps from an edge to a real number. And function d is a distance function that assigns a weight to an edge. And we could think about what such a function could look like. And what I want you is also, if there are some exams, if some questions like this come up in an exam, I want you to use the notation we are discussing here in the course. I don't want you to come up with your own definition, what a directed weighted graph could look like. There could be some way to put the weight into this E and amend what E could look like from its structure, but E will just look as before. It's the directions. For the weights, we will have a new function that is separated. And as an example down here, our function d could look something like this. We say d of E of a concrete edge is a partially defined function. We can say it is value 3 when our E is 1, 2. So this would be 3 if our edge goes from 1 to 2. We can say it's 2 if our edge is 2 to 1. And I'll quickly want you to think about what this graph may look like. And I will also add a loop on top. We are adding a loop into the 4, and we say this one is, say, 10. Remaining steps, or the remaining definition of our concrete function d, one student says we have somewhere else a distance of 2. I will, in the first one, just write out it's 2 when E is from 4 to 3. You could obviously somehow merge these two lines if you want and say it's 2 if E is the one thing or the other one. But for now, I just keep this out. Then one student sent something here. It's what you've sent is something about the edges. We don't care about the edges. You know how to define the edges now. We've practiced this a few times. But I guess I know what you mean. If this is from the two edges with a set, we could do that, yes. We can say it's 4 for the edge that is from 2 to 3. We can say it's 1 if it's the edge from 3 to 4. And there's one missing. What would the next one look like? For the loop, any suggestions what I would need to put in this definition? We would say it's 10 if the edge is 4, 4. So this would be a partially defined function, which is one way how we can define D. There are other ways how we could define D, obviously, but I just like something like this, which makes it fairly easy to understand if someone looks at it. Before we finish our directed weighted graphs, I want you to think about, for our sample graph here, what its adjacency matrix may look like. So we have 4 vertices, 1, 2, 3, and 4, and we say the row is from and the column is to. I will start with the first one. Going from 1 to 2 has weight 3. So I put a 3 in here. Going from 2 to 1 has weight 2. And I want you to think about how to complete this matrix. And if you have any entries for this matrix, just send it here. And I saw the other question in the chat about how to define this function D. We'll look at that in a moment. But I'll wait for you to think about the adjacency matrix. So going from 2 to 3 is the next one, which has weight 4. Then 3 goes to 4, which has weight 1. 4 goes to 3, which has weight 2. And the loop in 4 is 10. And all the other entries are 0. So something like this. There is, in one of the answers in the chat, the person should pay more attention to the second row. So we say 2 goes to 2, 2 goes to 1 and 2 goes to 3. One person has put something into here. That would mean there was a loop in 2, but there's no loop, so maybe just check your response in the chat. There's the question, if a graph can have a weighted and non-weighted edges at the same time. If they're not weighted, you would just put 1 usually, and then the other weights. So this is how you would combine this. 1 would just be the normal weight or no specific weight, and all the others would be different, and you would maybe normalize it like this, that it works. There was one person in the chat who asked if you can write this here slightly different and suggested if you could write E1, 2 or E2, 1. I'm personally not too happy with such a notation because E would look like a function, but E is not a function. Rather, E is a tuple, and we want to see if the tuple is that specific one or not. So that was one of the questions in the chat about how this could be typeset. I would very much prefer you to use this proper notation here, so we actually know what it means. So we will quickly go back to the slides. All what we had just discussed is also well typeset in the slides, like undirected graphs, permitting loops, directed graphs, permitting loops, directed weighted graphs, permitting loops. And we looked at such an example here, and slightly amended it with another loop. So it's all well typeset. Last week we looked into applications of graphs in computer science. As I said, there are other data structures that are just some variation of a graph, and there are numerous graph algorithms that we deal with. And most of the algorithms in this course are eventually some sort of graph algorithm, because lists and trees are graphs with some constraints, and we write algorithms that work on these data structures. What we will do next now is we will look at an algorithm that is called shortest path. And shortest path is something that is discussed in a lot of algorithms and data structures courses with lots of variations. There's, for example, the Dijkstra algorithm, which is one variation thereof, and there are numerous algorithms. So the idea of shortest path is you want to find a route in a graph to get the quickest from one city to the other. Sometimes this is called the Dijkstra algorithm, but in this course, we will discuss this a little bit differently. We will first start with a shortest path algorithm that works on graphs that are not weighted, so it's just hops from one city to another. And when we have weighted graphs, we will later look at the lowest cost algorithm. So we define this a little bit differently, but you will see very soon why. And our algorithm here that we built, shortest path, has a huge advantage. It's an algorithm that not only works for routing, but in fact, it works for generic state search problems. And this algorithm can be used and applied to numerous problems, which are not just routing, but plenty of other problems as well. So the shortest path algorithm we discuss here, you will not find this in the book. It's rather a collection from outside the book, and I've amended it a little bit to make it work for this course. It's a search algorithm on a graph to find the shortest path from a start state to a goal state. So the start in routing could be the start of a city, and the goal is you want to go to a specific city and you want to find the shortest route. But it also introduces one word here. It says it's an uninformed search algorithm. And uninformed here means the graph is not weighted, so we don't have weights in the directions. Rather, all the weights are the same, which are just one. Later, when we look at lowest cost, this would be then probably called an informed search algorithm, for which we have weights. But we ignore weights, we just look at connections between nodes for now. And we want to find the shortest path in terms of the number of path elements which have a uniform cost. So all the path elements, the weights are uniform, the same. And there's another word, so it's a little bit of terminology. Then we look at some examples, and then we see how to implement this. Each state might have a number of successors. So the numbers of a state, the successors of a state are the states to which our state is connected. And we certainly have a directed graph here. It's not like not necessarily an undirected graph. It works for a directed one. And we will implement this algorithm very soon. And it will have three parameters: the start state, the successors function, and an isGoal function. But before we draft the algorithm, I want to know from you, are you all familiar with function references? Do you know what a function reference is in programming? Maybe thumbs up, green sticker, if you know what function references are, or red sticker if you just don't know what that is, which is also perfectly fine because we didn't do this in the intro to Python. So before we look at the algorithm, we will look at function references. And it's something that you can do in certain languages and something you cannot do in other languages. We will test this out in our interactive environment. I will have a function f now, and my function f has a parameter a, and all it does is it prints the value of a. Nothing specific, nothing very sophisticated. So for f, we pass a parameter a, and we print it. So we can pass value 5 to f. This is something you have all done so far. But now I can do something new. I can say def main function, and for the main function, I pass a reference, which I call function reference. So I have a parameter function reference, and parameters you have seen so far in coding are typically like values, like an integer or string or an object, and you work with it. But this time, we're actually passing a reference to a function. And this function reference is just a variable that refers to this function, and we want to call the function to which our reference refers. And at the end, we can add some prints maybe. We say print calling function, and here we would print function was called. If I try to just run main function and not pass any parameter, this will not work because I need to pass a reference to my main function. And the way I will do this is I put the name of the function for which I want to pass a reference. I put that one as a parameter. It's very important. I'm not calling f, but I'm passing f as a function reference to main function. And in main function, we pass the function reference. We do the first print calling function. Then we call the function to which function reference is referring, which would print some value. And we would then say function was called. This is the idea. It doesn't work yet because my main function calls a function reference. And for now, well, we can test it for now and we'll just see what happens because it doesn't work yet. But we call main function and pass f, and we try to run it, and it says, oh, it doesn't work because we pass f, and f gets called here, but in order to call f, we need to pass a parameter. So, and then here f gets called without a parameter, and this will lead to an error. So we can amend this and we say, well, we pass value 100 to any function that gets passed. And this only works for a function that would accept one parameter. But now I'm passing f as a function reference to main function. Calling function gets printed. Function was called at the end, and then in between f is called with value 100. And what I see is this one here. What it prints is calling function, this one. Then f is called with value 100, and the last print happens. And I can pass other functions. I can now define, for example, function 2, which is a, and then what it prints is maybe the square of our value. And I can pass the reference to f2, and f2 does not print 100 then, but rather 10,000. So this is a highly flexible approach. I'm passing a reference to a function, and that function gets eventually called. So some of you have seen this before. Maybe some of you want to tell us quickly in the chat or turn on your mic what you have used function references for so far, or in which language you have dealt with something like this. I'll see if anyone responds, or you can also just turn on your mic because some of you sent a reaction before that you are actually familiar with function references. And there's a question here if this is something like making f a global function. So yes, f has global context because we define it in the global context, but it is a global function anyway in this module, no matter if it has nothing to do with the function reference. I've just defined it here. And so I have defined f2 or main function. All of them have global context. One person has used C++ to pass a function which would be called for each vertex of a graph, okay? Someone else has used JavaScript, some sorting functions for objects that can take a comparison function of how to compare objects. This is really cool. This is something we will also see in the sorting chapter in a month or in 5 or 6 weeks, whenever. When we look into sorting, we see we can also pass a parameter for comparison in which we define how objects actually relate to each other in terms of their order. And this can be done, for example, with a function reference. So, but this is something we'll see when we actually look into sorting. So we have now looked into our function references, and we will need these function references very soon. But first, we will look into our algorithm now that we want to build, and we start actually with an example. And then I'll show you how such a graph would look like. And from there, we will try to implement these algorithms. Somehow the screen share failed, should be working very soon. So it's back. I will provide you with an example because we said we need a couple of things in our algorithm. We will need, in the shortest path algorithm, the following. We'll need a start state. We will need a successor function. And an isGoal function, or just goal function for now, that would tell us if a specific state is actually the goal I'm looking for. And I will show you this with an example, with a very small example, and then we will implement this. Let's imagine we have the following graph. We have one is a state, can be a city, can be some other state. It's just a generic state problem. You can always initially try to understand this from a routing perspective, and later we will actually do more complex stuff and not just routing. We say there is a state 2 and a state 3 and state 4 and a state 5. And these states are connected. So, for example, 1 has a successor state 3, 1 has a successor state 2, 2 has successor state 5, or 2 is connected to 5, 3 is connected to 4, and 4 is connected to 5. And, for example, 2 is also connected to 3, and 3 would be connected to 1, and 4 would be connected to 3. It's just an example made up. And we will have a couple of things. We want to know a function. We say 5 is the goal, and 1 is the start. And we only have one action for now. Later, there may be multiple actions that you could take, but we just have one simple action for now, which is going from one state to the other. But we may have different actions. It could not just be going, it could be some other action. And later, when we look at generic state search, we will see there could be different types of actions. So not just that one action, but we just keep it simple for now with one action. And we also need something that is called the frontier. A frontier is an element of a search algorithm. And I'll quickly tell you orally what the frontier is. If you want to see a definition, it's also available in the slides. A frontier contains all non-visited successors of previously visited states. I will just write this out up here. So the frontier is contains all non-visited visited.
I think the screen sharing broke.
Okay, thank you. This is something that I don't notice. Sometimes the screen sharing on, so I've tried updating Zoom and sometimes the screen share works perfectly for 1 week and sometimes there are some issues. This is something I've tried with Zoom updates. I'm unable, unfortunately, to fully get this fixed. And in some years it works and some years it doesn't work. But if it just terminated, let me know. So what I said is the frontier contains all non-visited successors of previously visited states. This is an important definition, and it's also written very well in the slides. And what is key is also of non-visited successors. So once we have visited a state, we will actually not visit it again in such a problem. And we will look at how our shortest path may work simplified on this problem. We will also have another variable that we introduce. It's called explored. And explored means these are the states we have already looked into. We are starting with our start state. So we're now in the start state. We are starting with it. So one has been explored because we have just entered in one, which is our start state. And we will not come back to our start state from other states. And I want to ask you, which are the successors of our state one? Where does one point to? 2 and 3, that's correct. So these are the successors. And these successors are something that we will explore. We also have our variable frontier, and right now the frontier contains something. The frontier may contain later, once we run this on a real problem, may contain lots of elements. Initially, the frontier contains our start state when we start the algorithm. So we put our start state in the frontier, and explored is also, it's a list or set, and we say one is now explored because it's put in the frontier. We are starting with this. And now we continue our algorithm as long as there is something in the frontier. What is in the frontier? Exactly one element, which is 1. So we are taking this away from the frontier, and it will be our working state. So once we take something from the frontier, we remove it. So we just, well, we actually cross it out. We will implement all of this very neatly later. So it's just an initial discussion. We'll see some more details later. And we will look at the successors of our states. Sorry, what are the successors of that element we just picked from the frontier, which are 2 and 3. And then we can say, well, let's look at 2. And 2 is a state that so far has not been explored yet. So 2 is not in explored. So we can put, and we can also check at the current stage. So since 2 has not been explored yet, we can see if 2 is actually our goal. And it's not our goal. So we can say 2 has been explored, and we can also say we can put 2 in our frontier. 3 was a successor of 1 as well, and 3 has not been explored yet. So we can add 3 to our frontier as well, and we always add to the right of the frontier. Now we have looked at all the successors of 1. So we're done with 1. And initially, in the very beginning of the algorithm, we would also look if our 1 is actually the goal, which is not the case. Now we still have something left in the frontier. So we actually pick the 2 from our frontier. And because we pick it from the frontier, it's disappearing. And what are the successors of 2? And I'm adding one more. Just wait a second. Like this, just to make it more interesting. What are the successors of 2 now? Send this to the chat. It's 1, 3, and 5. We start with 1, but 1 was already explored. So it was. Another successor of 2 is the 3, but 3 was already explored and added to the frontier, and we don't want to add it again. But another successor of the 2 is 5. And 5 has not been explored yet. So we can actually add this to explored. And before I also said orally 3 was also explored because, so I've just added this to our set, because when we looked at the neighbors of or successors of 1, we looked at 2 and 3, and we said they are explored. We've added them to the frontier. And now from 2, we looked at its successors, which are 1, 3, and 5. 1 and 3 were already explored. We can ignore. And 5 is something we are adding to the frontier. And 5 is also now added to the frontier. And our 2 that we looked at, 2 is also not the goal. So because 2 was not the goal, we continued with all of this. Now we have 3. And 3 has various successors. Which ones are the successors of 3? There are a few questions. I will answer them later. 3 was explored because 3 was a successor of 1. And when we added something to the frontier, we said it's explored at that moment. We will still pick it from the frontier, but we will not go there again from a different route later. But later we will code this up and then it will all become clear. It's just a simplification a little bit. We'll bring in more structure soon. So 3 has 2 successors, 1 and 4. 1 was already explored. We don't care about it. And 4 was not explored yet. So we are adding 4 to our frontier. And then we put it in explored because it's now in our frontier. And when we looked at 3 from the frontier, we removed it because we said when we take one element from the frontier, we always take the leftmost element and remove it. Now we've looked at the successors of 3. We've added the 4 to our frontier. Now we are picking 5, which is the leftmost element left in the frontier. And we see 5 is actually the goal. So we are done. Because we have now found the shortest path from 1 to 5, which is 2 hops, 1 hop to 2, and a hop from 2 to 5. Whatever is left in the frontier will not give us a shorter path anymore. So we don't need to look at now any possible successors of 5. 5 is our goal. We are done. There was a question in the chat, why we put first 2 and then 3. Could we put this vice versa? Yes. So when you look at the successors, say the successors of 1, we said it's the successors 2 and 3. We could, but it's a set. You can also say it's successor 3 and 2. So it doesn't make a difference if you first pick 2 and then 3 or 3 and 2. The algorithm will still give you the shortest path. But this was just a little bit simplified to show you a little bit of the idea what this algorithm is about. And I think it will help us to implement it. And then we will actually test it on a real problem. What you will see is, I'm doing the screen share very soon. And there's a question why we can't stop yet when 5 is already in the frontier. There are some technical reasons for this, because we first add new stuff into the frontier, and later when we crap it from the frontier, we will explore it, because we also want the proper paths in our frontier, because the frontier we are building now will be a bit more complex. It will actually contain whole paths and not just single states, but all of this will be implemented now, and step by step it will become more clear. What I want is the shortest path search. And we said our shortest path search has 3 parameters: start, successors, and a goal function. And we call the function isGoal. So the type of parameters is something very crucial here, because start is a state, successors is a function reference, and isGoal is also a function reference. First of all, and we don't know what the isGoal and the successors function look like. We will later discuss why we don't care about what they look like when we discuss the advantages of this algorithm. But it's simply a function that must be implemented for a concrete use case, say for our routing problem or for some other state search problem. But it's a function reference, and when I use it, I assume it's properly implemented. So I can say, I have a start state. I want to check if isGoal is a start state. If so, I need to return something. I could just return true, but actually I want to return the shortest path. So not just a yes, no, but the whole path. So I could think I'm just returning start. But start is a single state. And from this function, I always want to return a list. So I put start in state, start in a list. So I'm just putting the brackets around it, and I'm returning actually a list. So the list would only have one element, but later we will have a whole path in the frontier, and we will return entire paths. So rather, we always return paths and not just a state in this exceptional case here. Then we need our helpers. One is explored. We could just say, well, explored is a list of the elements we have already explored. And we've just explored the start state, so we don't need it further. But later we need to do efficient lookups in our list. And we want to see, is there some state that was already explored? Not too efficient, there is a data structure which is called a set. And with a set, we can do something like this very efficiently. We can do a lookup. So what I have here, it's a list that only contains our start state, and I'm converting it to a set. And later I'm adding to this set, because I need to do efficient lookups of what has already been explored. The next one is our frontier. And the frontier, we said, should contain in the very beginning, and what I've shown you, the example, was just a little bit of a motivation, and we will bring in some more structure now and make sure it also works in some edge cases. So what I'm typing now is maybe here and there slightly different to the example before, but the example before was just to motivate all of this, and now we will formalize it. So we said, initially, when we start the algorithm, we need to put something in the frontier, which is the start state. And we can say the frontier is a list. And there's a question here if you can also use a set notation in Python, something like this to define a set. Yes, you can do that, but I just write it out set for the beginning today. And there's a question if the interface appeared too small with you, with the screen share, should actually be fine, but I can make my window a bit smaller. Something like this. Does this look better for the one who said that you can barely read anything? Now we have this distortion here from resizing, but I hope it looks better for you now. So we said our start state was put in the frontier, but later when we implement this, our frontier will not just contain actual states, but actual paths, how to get from one state to another, actually also taking a concrete action. But we'll see this. So what we do is we actually say we want a path, and the path will always be represented as a list. So our start state is put in a list, and that list is the first path that we will explore. But the frontier may contain multiple paths, so it's a list of a list, and the list is the actual frontier, and inside there are paths, and each path is a list as well. So I know this algorithm is not easy because it's a highly generic search algorithm, and we will later discuss why it's so helpful compared to other approaches. But it's highly generic, so it takes a little bit to understand, but it's a very good exercise to also learn more Python. Now I have a while loop, and this while loop will run as long as there is still something in the frontier. Right now, we just put one list in the frontier, so there is something. And later, we may add more elements to the list, as you saw in the simplified example. But it will become, maybe over time, the frontier will grow a lot and then shrink. And within this loop, we will do tests whether we have actually arrived at the goal. If we find this, we will return a solution or a path. And if this loop ever finishes, that means the frontier is empty, but no solution was found to our problem. So we also need to return something later. We've said we always need the leftmost element from the frontier because we add to the right of the frontier, and we always take the element in the frontier that has been there the longest. So we take the leftmost element, and this can actually be done super easily. We can pop just the leftmost element from the frontier. So this popping means give me the leftmost element, so the one with index 0, remove it from this list, from frontier, and return it to me. So it's stored or assigned to path. This is not a very efficient way how to do this in Python. When we look into lists in a few weeks, we will think about this again, if popping at element 0 is so smart or not, but we haven't explored lists in detail yet. So it's something that will come in a few weeks' time. And then later, what could happen in our frontier is we have a state in a path followed by an action, followed by a state, followed by an action, followed by a state, because we always go from one state to another with an action in between. So now I have a path which is in our beginning a list with just one element, but later there are more actions and states in it. So I actually want the last state in this path, and I want to expand this later. So I need to look into path, and I take the rightmost element. This is something we also saw in the intro to Python. If I use index -i in a list, it gives me the rightmost element. Now I know this is highly generic, and for you, in order to practice and understand in detail in your revision how this algorithm works, it's probably quite helpful if you also start debugging this algorithm. We something now. We need the successors function, because now we care about what's the successor function of that state S that I'm exploring. So I somehow need to call the successors function on S, and it will return me something. This here doesn't work yet from the syntax. Our successors function is represented as a dictionary. And on a dictionary, we can call the dot items function and call it, and the dot items function will return us something. And what it will return concretely is a tuple. And this tuple, we will later look into it and see a concrete example of what it looks like. The tuple that we get has two elements. And the first element is something we would call the state, and the next one, the action. Concretely, the state that we get is a tuple, and that tuple would be the key of the dictionary, and the action would be the value of the dictionary. So successors S returns me a dictionary. I will later implement these dictionaries, and we saw dictionaries last week. And when I call dot items on the dictionary, it will give me a tuple where the first element is a key and the next one is a value. And state is the key. So we call the key simply a state that we explore, and the action is our value in the dictionary. And we later see concrete dictionaries to make this happen. There was a question to explain again what S is. So I said, initially our frontier contains a list, which is a path of only one element. And later, when these paths grow, we keep adding actions to the path. So if we update this path, we would add an action and then another state, because we can take a specific action to get to some state. And I always want to take the most recent state in our path, which is the rightmost element. So I say path at position -1. And for that most recent state in the path, I call the successors function, which it returns me a dictionary by convention. Later, I still need to implement successors, obviously, and I call dot items. And dot items gives me key value pairs. This is the key, this is the value. And I'm calling the key state and the value action. Now I need to check if state has not been explored yet, because state is a successor state, and I only want to look at the ones that are not explored yet. So I can say in Python, if state is not explored yet, because explored is a set, so I can say if state is not in explored, and if it's not explored yet, I will edit and say, well, now state is getting explored. If state was already explored, we would just ignore that state. So everything we're implementing now is within this if, because we want to explore the state. So we say, well, we're exploring it now. And we need to find now a new, or we need to add a new path to the frontier. Before I said, I have my path, which is initially just a list with one element. But now I'm taking a concrete action, because there can be multiple actions. And in Python, you can do something very, very interesting. You can have a list, which is path, and you can write a plus sign with another list, and eventually this will concatenate you the list. So I say one list plus another list, and I will get a new list where I'm just appending these two elements to the original list, and I'm returning a new list. And this is my new path. So I can say path2 is my old path, which was initially just this list with the start element. and I'm taking an action which leads me to the next state, the successor state. Now I can check if that new state is a goal state, and if so, I'm returning this path. Because I was in some state, I took an action to get to the new state, and if that new state, to which I have a path, is a goal state, I'm done. If this new state is not a goal state, then I'm appending it to the end of the frontier. Frontier is a list, so I need to append this new path to the end, to the right end of the list. So we have almost built our algorithm. The only thing that can happen now is that we don't find a solution to our search problem. That there's just no solution to get from a start to a goal, taking these actions. And then if this while loop ever finishes, that means we have run out of elements in the frontier, then we have a problem because we couldn't find a solution. And then we need to return something which we would just say it's an empty list. And an empty list means there's no path from our goal, from our start to the goal. You are probably wondering why we implemented this algorithm this way. Because we talked the whole time about routing, and we said we get from one state or from one city to another city, and we want to get the lowest number of hops. There's a reason for this, why we're doing this. We are using the shortest path algorithm, and you see it has nothing to do with routing. It's just a state search algorithm where we think in terms of states, and the states could be a city, but states could also have multiple elements. We just don't care what the state looks like. All we need for the state format is an adequate successors and an adequate goal function. Because if you solve such search problems on your own, I don't know, have you ever implemented like a search algorithm to search through a maze to get from the entry to the goal? Maybe send me a thumbs up, thumbs down if you have ever implemented something like this, or some other search algorithm. What often happens is you merge two things in such an algorithm. You merge the actual search with your actual problem. And if you do that, typically such algorithms don't work very well because you merge the actual search with the actual problem. You're merging two things that actually don't fit together. So you can hardly reuse such code, and debugging it and fixing it is often very, very bothering. What we have just built is, so one person says you have done the same thing. So do you mean the same thing that you have separated the search from the actual problem for the one who wrote this in the chat? And if you have done that, that's very, very smart, because what we have built is it's a very generic search algorithm. And for our concrete problems, we define a state format, a successors function, and a goal function. So we never need to think about search again when we use this function. We only need to think about problem-specific state formats, successors function, and goal functions. And then we plug this in as function references, the successors and is goal, and we run it. So it's highly generic, and it even works for multiple actions. Before, we've only seen one action, which is walking from one city to another. But in some optimization problem, you may have plenty of different actions you could take. One student writes that he does not understand the interest using a set because we can search within a list too. Yes, you could see explored also as a list. That's perfectly fine. But when you want to do a lookup in a set, this is implemented in Python very efficiently. You could go through your explored list and figure out if something is in that list. Yes, but it's inefficient because the set is specifically made for efficient lookups. Later in this course, we will look into different data structures that allow efficient lookups. We will see, for example, hash tables, trees. We briefly talk about sets. They are all much better in terms of their complexity than and running time than a list when you do lookups. But this is something we'll discuss in a few weeks. But we just want to get it right from the beginning. So bear with me that a set here makes more sense. And after we have implemented this algorithm, we will quickly. There was a question to recap the code. I'm not doing this now because we will actually apply this code now, and then it probably becomes more obvious, and then we can recap it. So I told you what a frontier is. It contains all the non-visited successors of previously visited states. And concretely, it is also sorted by path length in an ascending order. So to the left, we have the oldest elements with the shortest path length. And when we add something to the right, by appending to the frontier, we actually have longer paths. Visited states will not be visited again, and we always pick the leftmost element from the frontier and expand it, meaning we go through its successors. And the successor may be a goal state, maybe not. And the algorithm returns the successful path, which is a start state, an action, the next state, an action, and another state. And we've implemented this algorithm. There was just the wish to recap it, which I'm not doing now. We will apply it, and then we can recap it. What I did in my implementation is I returned an empty list here. In these slides, I'm returning fail, and fail is simply defined as an empty list. But you could also, this is just to highlight that a fail is an empty list, but I just merged this in my implementation. By the way, in our Nextcloud, we have this resources.zip file where we have lots of code snippets that we need throughout the course. Feel free to look into this. Don't try to copy paste this stuff from the PDF, because this typically leads to formatting issues and it will not work. If you want to reuse my code, please use this resources file where it's all in. You just need to open the zip file, and you don't need to try to copy paste this from the slides. We will now look into an application of our shortest path search. Before, you have seen we can use it for routing, but we can also use it for the so-called pouring problem as one example, which is also in the coursework. But I want to discuss that coursework problem with you now, because this will help us to better understand the algorithm. And trying the screen share again. So. We will look at an example, which is the pouring problem. In the pouring problem, we will have two classes. We have one class and a second class, and they have a certain capacity. For example, this one has capacity 418, and this one has capacity 986, for example, in milliliters. And we are starting with classes empty, and we have a couple of actions that we are allowed to do. We are allowed to completely fill a class. We are allowed to completely empty a class, or we are allowed to pour from one class into the other, but only as much as possible of one class into the other one. So we are not suddenly, so imagine we have, just as one example, we have like 300 in here. So we would be allowed to pour those 300 into the class, but not like 250 or something. We are allowed to fill a class, maybe as the first setting, we're allowed to fully fill the left class with 418. In those 418, we're allowed to pour into the right class, but only the 418, not more, not less. But if the class on the right has maybe already 800 filled, we are not allowed to pour the 418 in and partially over. So we are only allowed to pour as much as possible so that the right class would be full and we keep the remaining water in the left class. One action is also, so actions that we allowed is already said to totally fill a class, to totally empty a class, or to pour as much as possible. And I want to do these actions, and I actually have a goal. And my goal is I want to get to 6 and 0. So the actions are, again, I'm allowed to fully fill a class, the left or the right one, empty the classes entirely, or pour as much as possible. So not just pour 6 from one class to another, but what is completely in this class, or in order to fully fill the other class and keep the remaining water in the other class. Are you okay with those rules? Maybe give me a thumbs up or thumbs down if you're okay with these rules. What do you think? How many actions? So these are different actions, because before in the routing problem, I said we will look into problems where we are allowed to take multiple actions. And here we have different actions from one state to another. So one state is the start state, and we have a goal state. And from the start state, we could take different actions, like completely fill, completely empty, but this doesn't work because there's already something in. But we could completely fill the left class, or we could completely fill the right class. So different actions that lead to different states. And one student guesses that getting from 0, 0 to 6, 0 would take something like 500 to 1,000 steps. Who thinks this is realistic? If you think 500 to 1,000 steps is somehow realistic, maybe thumbs up. If you think this doesn't make any sense, could be done with far less steps, maybe a red sticker. So there's a large number of disagreements. So the question is it that many steps? We will see later. Because we will implement all of this now on our own. And the good thing is we don't need to implement the actual algorithm for this because we already have our algorithm. What we have is we have a start state. So we can say the start state, our states are now tuples, which are the filling level of the left and the right class. So I say my start state is 0, 0. I also need an isGoal function. So we can say isFull is my function, and I'm passing to isFull a state, and it would return, it would check if some state that I'm passing is equal to 6, 0. And this would always return yes or no. Are you okay with these two things we have just defined? We have defined the start state and our state format and our isFull function, which would be the reference for isGoal. Maybe thumbs up, thumbs down if you're here with me. So what do we need to define next? One student asked to say again, so I want to use the shortest path search to solve our pouring problem. Because we have a start state and now a goal function, because we want to get from 0, 0 to 6, 0. But we still need to think about the different actions and the consequences on states. So what is the last thing we need to define now in order to solve the pouring problem with the shortest path search? The successors, that's correct. So we will say successors. It's our successors function. And what we do in there is we will have a state that gets passed. And because you see in here, and this, we will now go back to the algorithm step by step, also for a recap. We are passing a start state, and you see our algorithm knows nothing about the state format, because it could be a tuple, could be a triple, or some totally different objects. The shortest path search has nothing to do with that. So we have a start state, we have an isGoal function, which gets called here, again, only with a state. And the successors function gets called with a state. Now, what I also need is I somehow should define my capacities. So the maximum filling capacity of these classes, which we said the left class, we say a capital X is 418 and a uppercase Y is 986. And I have my state, which is a tuple. And in Python, you can do something very interesting. You cannot do in a lot of other languages. I have a tuple state, and I can break it into its two components. So X will be the left element in the tuple, and Y will be the right element in the tuple. Has any one of you ever seen something like this in Python? Maybe thumbs up or something if you have ever seen something like this. Good. And today we will need maybe 15 to 30 minutes longer, but then you're well prepared for the coursework. And since the class is officially over in a few minutes, if you're leaving, the recording will be uploaded of the remaining 30 minutes in YouTube later tonight. Not immediately after class, because I need to rush to a meeting, but it will appear before midnight in YouTube. But then you have all the tools you need for next week's coursework, because if we stop now, next week's coursework you wouldn't be able to do yet. And we are already partially exploring next week's coursework together, which is about this pouring problem. And I want to enable you to do this and to also do the other coursework. So we will need maybe half an hour longer. We'll see how long it takes. But then you're well prepared for the course. And it's Friday evening, so you don't have any other class next. What we could also check just as a small thing is just that we don't run, like we will build now a complex successors function. It could happen that we just have some logic error in our successors function. And in order to catch such stuff, we will just check if our capacities or the filling levels in the state are actually valid values. And for this, we have assert statements in many programming languages. They check this condition. If the condition is fulfilled, it's fine. However, if it's not fulfilled, the program will terminate with an exception. And we know the filling of the left class, which is the small x, must be less than or equal to its capacity, 418, and the small y needs to be less than or equal to capital Y, because you cannot have more in the class than you're allowed to have. Now, we need to build a dictionary. And this dictionary, there are lots of ways how we can build this dictionary. We can say, for example, result is a dictionary, and we are adding something to result. Concretely, we're adding a state as the key and a corresponding value like this as an action. So I want to say, I want to fill X, and probably I need, like this in Python. So I'm adding a new state in order to fully fill X, so the left one. I'll show you what this can look like. I say, no matter what is filled in the left class, I'm putting the maximum capacity in. So a capital X and a lowercase y, because the lowercase y is what I got from the state, and I'm only completely filling the left class. So I have filled the left class. How would I write that I want to fill the left class? Sorry, the right class. So I want to say, how do I fill the right class? Fill y. It's correct. I'm using a tuple x, lowercase, and capital Y. I want to do another one. I want to empty X. What do I need to do to fully empty the left class? Let's see. Someone suggests a 0. Is a 0 enough? No, I need a Y because I'm not changing, because I need a valid state and I'm just changing the left class. And in order to empty Y, what would be emptying Y? X 0. Empty Y. So we've done the easiest operations so far. Our dictionary, however, we will use a slightly different format. So we want to return our result dictionary, but we will use a slightly different notation. We will say we are building the dictionary. So I'm just developing what you will later see also in the coursework. We're just building the dictionary in one go and not step by step. We've just built it step by step, and this is something you can also do in some of your problems, that you actually build this step by step and maybe have some conditions before this step by step, but we will soon see how we can use conditions here as well. So all I've been building here is just amending it a bit from the syntax, that we are building one big dictionary step by step. It's not done yet. We will do it like this. So I've just added the key value pairs in one big dictionary rather than building the dictionary step by step, but we have not really changed anything to before. Just looks slightly different with the syntax. Now we will have two very complex things to do. We need to be able to pour from the left to the right class or from the right class to the left, but only as much as possible. We can imagine, so I'm already writing this now. I say I want to pour from left to right, so from Y to X. How can I do this? Imagine we have the simple case that we can pour everything from the left to the right class. So it's fully possible to move everything from left to right. Which tuple would you write? 0 and then, for example, Y plus X. Yes, that's fine. Because the left class will be empty, but we're not always able to do this, because sometimes we just cannot pour everything, but the class may actually be full. So we can only pour as much as possible. So we can only do this if the sum of Y and X is less than or equal to the capacity of the right class. So this is a condition that we sum Y and X. If it is less than or equal to what fits at the most in the right class, I'm fine. But if this is not the case, I need to do something different. And here I need a little bit of maths. Say, I can pour a bit from the left to the right, so the right class will be full. So the second component is a capital Y. The right class will be full. But the left class will still have something left. And what I can take is I have X and I need to subtract what I'm actually able to pour. So Y is the maximum capacity of the right class, and lowercase y is the current filling of the right class. And the difference of this is what I'm able to pour. So this is left, what is left in the right class. And I'm subtracting that difference from the left class. This is how much I'm able to pour. And then the right class is full. That's why we have the uppercase Y. Is this formula clear to you? Send me some reactions. So only positive. Now we're doing the last part and then we're already done. And then we will run all of this code and see why it works this way. I need to be able to pour from the right class to the left. What could this look like in the simplest case? Pouring from the right to the left class. In the easiest case would mean X plus Y is in the left class and the right class is empty. And we can do this if X plus Y is less than or equal to capital X. And this is also someone asked to explain the previous line again. Like in the previous line, we said we are able to move everything from the from the left to the right class. If we fulfill this condition, the left class is empty and the sum of Y and X is in the right class. However, if I'm unable to pour everything from the left to the right class, then the right class is completely full. And the left class, we are able to remove the difference of what still fits into the right class. In the right class, its capacity is capital Y, its current filling is lowercase y, and the difference is what I'm able to pour, and the difference is the one I'm subtracting. Someone asks here if you can use some other equations. Possibly, yes. The ones that were proposed in the chat, honestly, I would need to review them, or you can test them on your own because you're using the min function and this. Maybe this is possible, I don't know. I would also need to check these formulas. You can send them by email to me and I'm happy to review them, or we test them, we plug them in here, but I'm unable to see 4 lines of formulas if they are correct. But we need to finish the last rule, pouring from the right to the left class. If we can fully pour, so X plus Y is less than X, capital X, we move everything from right to left. And what would be the last part where I'm only able to pour part of it? Any suggestions for the equation? Capital X, so the left class is full, and we are able to remove the difference from the right class. And the difference is of what is still free in the left class, and I subtract that. So there is now a syntax error, and I don't see the syntax error right now, unfortunately, but I found it. There's a comma missing. This is a live demo, so sometimes there are, unfortunately, syntax errors, but now it's fine. So we will run the shortest path on all of this now. So I will store the result in S. I'm calling the shortest path. On the start function, I'm passing the successors function. And so we call this start state in this example here. So start state, successors, and is full. Let's see if it runs or if there's any error in here. It has run. Someone guessed it's 500 to 1000 steps. Let's look at the length of this. How many elements are in res? It's 1237. But this doesn't mean it's the number of steps. We can just look at the first 10 elements in res. And what we see in res is it's a start state, then an action, then the next state, then an action. So we actually, the length of res does not give us the number of actions, but rather we need to divide it by 2, and we see it's like 618 steps. This, just one note in Python, this is an integer division. If you're from the Java world and you do 5 divided by 2 in Java, what's the result in Java when you say 5 divided by 2? Maybe that's a revision of your Java or C++ skills. What is 5 divided by 2 in Java? Send it to the chat, please. It's 2. In Python, it was like this until Python 2. But in Python 3, this has become a floating point division. So if you want an integer division in Python 3, you need to add 2 of the slashes. So that's why I said length of res divided by 2. It's an integer division, so we round it down. That means we have 618 actions. So one student suggested 500 to 1,000 steps. Congratulations to you. You actually estimated that well. And what do these actions look like? We can just print res and we see it's a lot of work that needs to be done. We started with empty classes, then we filled the right class, then we moved as much as possible from the right to the left class. We emptied the left class, we moved again, and many, many steps, and eventually it's 618 steps. We can try out something now. We can say, we just pick some other problem. We pick, for example, a different start state. We pick a start state which is 4 and 3. And here I can just pass the actual state because this is my format, but it's ideally not a list, but rather a tuple. And we don't want to print this, but rather its length. Hope this is fine from the syntax. Something did not work out. I don't know if I have a parenthesis too much. So there is wrong that I'm unable to identify right now, but probably it's a minor mistake that was made. If any one of you sees what went wrong, because I found it. It's this one here. Now it works. So if I start with the start state 4-3 rather than 0-0, it only takes 63 actions to find the lowest path. So you can play with this on your own in order to test this. For the last 5 to 10 minutes, there are a few more Python hacks. And then you will see actually the exact version we have in your coursework problem. One thing is we have used the res function, we said we call the start state, or we pass the start state, we use the successors function and the isFull function. Who of you knows what a lump, and remember, the isFull function was this. We passed the state and we checked if the state is 6-0. Who of you has ever come across a lambda function? Maybe thumbs up, thumbs down if you know what a lambda function is, or green or red. A lambda function is an implicit function. So I had to define my function isFull, and eventually it's not doing much. Some programming languages, they offer lambda functions. And a lambda function would look like this. So it's an implicit function. rather than passing a function reference to this is full, I'm creating a lambda expression, and Python will pass the function reference to this lambda expression. This lambda expression eventually says it's an implicit function. I'm passing one parameter state, and I'm checking if state is 6-0. All of this behaves as before. The only advantage is I don't need to separately define this isFull function, but rather I can just use this one here, and we can also, since we don't need a print function on the terminal, we can also just do it like this. So it still behaves like before, 618. And we can also say, well, we had our, I think it was 4.3 or something before, which we pass now as a state. So it's 263. And you could also, I don't know, try out something like this. We want to get from 4.3 to 6.11. How many actions does this take? The result of our path is 0. And 0 means there's no possible path to get from 4.3 to 6.11. You can think about why this is not possible. It's actually quite easy because our two filling capacities are 418 and 986. They are both even, they are not odd. Well, I'm starting with this odd one here, but it still doesn't work to get to 6.11. So there's no possible path through our graph. And there's one more Python hack. We will get back to this successors function. We've implemented the successors function before, and when you look at the coursework, the successors function looks different. What this successors function does is we say we analyze our state, and these are the capacities. But actually, it would be quite interesting to manipulate these capacities easily too without changing this whole function. So I want to change capital X and capital Y. How can I do this? I could make X and Y global parameters. So I could store them in a global context. I cannot just add them as a parameter to successors, because successors gets called in our generic stage search. So I'm not able to amend it there. And what I've shown, what you will see in the coursework is, I'm doing a little hack. My successors function will look different now. It's an outer function for which I have these parameters X and Y. But since the signature has changed, I'm unable to pass successors now in the shortest path search. Rather, I am building a function within a function. Has any one of you ever seen this? A function within a function? Maybe thumbs up, thumbs down. It's something you can do in Python. Something you cannot do in Java, I guess. So within my successors, I'm creating a new helper function that I call SC. And SC is the actual successors function we want to be using. Now I have a function in a function. So I need to indent correctly. That's something we discussed last week. Indenting is super important. And if you don't indent, it will not work. What am I doing here? I have a function that is called successors, where I now have x, y as parameters. And within the function, I have a subfunction that I call SC. And SC is just the successors function from before. I pass a state. I'm checking if I am decomposing the state. I'm checking if the state is valid. I'm building my dictionary, and I built the dictionary like this, but I could also just return my dictionary if I wish directly here. So I don't need a temporary or local variable for this. I'm returning directly in the inner function the dictionary, and this dictionary is the one that gets processed. And when I'm calling the outer function, I'm not calling the inner function, but I'm returning a reference to the inner function. This is something you should definitely run in the debugger. And what I can do then is, when I call my shortest path, say on the original problem, 6, 0, I'm now not passing the reference to successors, because successors is now this outer function, but rather I'm calling successors with these capacities. And when I'm calling successors with these parameters for x and y, it will return a reference to the inner function. And this reference to the inner function is the one that is actually passed into the shortest path and will be called by the shortest path as the successor function. But this internal successors function, SC, can use x and y, and I don't need to make x and y program-wide global variables. That's something that we try to avoid. That's why I'm passing my start state like 4, 3. I can customize here very easily these capacities, and I have this lambda function, and I'm running it, and it's 263 for when I'm starting with when I'm starting with 4, 3, and I want to get to 6, 0. 611 will still not work, so I can easily amend this here without amending all these functions. And I could, for example, say it's 418 and 985. Still not possible. Maybe we say 21, 985. So you see, our pouring problem just doesn't seem to be solvable. Maybe you can try at home, in order for this pouring problem to be solvable, find some capacities where this is actually possible. I've just changed the goal state, and you see, getting from 4.3 to 6.0 using these capacities takes me 97 actions. This algorithm is something you should revise at home and run it in a debugger, because we pass a start state, a reference to the successors function, and the isGoal function. IsGoal is called in here, and the successors function is called on a concrete state, which returns a dictionary. And the dictionary, on that one, we call the items function. This is something that comes natively from Python. And what it returns are key value pairs. And the key we call state, and the value action. And this is what we saw here. These are the keys, the states, and which are the keys, and the values are the actions. So keys are the states, values are the action. Now that you've seen a concrete example, it's probably far easier for you to understand this, but spend time on debugging. And just quickly on the slides. So we said we have this problem, and yes, we have 618 actions that it takes. We've just tested it. And we've seen now one approach to shortest path that is highly generic. We can use it for routing, we can use it for this optimization problem, and for lots of other optimization problems. And the coursework for next week in the lab is problem 7.11. We've just solved the coursework together. That's why we've taken now another half an hour to solve the coursework together for the next lab. But until the next lab, you should still spend enough time on this in order to debug it and understand again what's the outer function, what's the inner function. And for all of this, a debugger is helpful. And here in the lecture, we have already filled in these four states, which you didn't see here, but we have already solved it together. And then there's problem 7.2. It's another application for our shortest path algorithm about the so-called missionaries and cannibals. And what you can do is you can try to understand this problem and apply the shortest path search to it. For that one, your states will look different. Your states will have 5 or more entries, not just 2 entries, because you will have a number of missionaries and cannibals on the left and right, and you need to keep track of where that boat is on the river, read the problem, and you will need a more complex state format, and you will need a more complex or slightly more complex goal function, and a way more complex successors function. And there will be lots of rules in it. So maybe don't build one big dictionary in one go for 7.2. Rather, build an empty dictionary and then have some rules with if else, and based on the conditions, add some elements to your dictionary or not, and return the dictionary eventually. But for the missionaries and cannibals, you don't need such an outer function. You will just use a successors function as we have built it initially today, which you find in the recording. And you would just pass the reference to the successors function. You don't need parameters for your successor function because the successors function will just work on the state, and you don't need this inner and outer function. Just a simple function as before. Last 2 slides on the shortest path. So next week we'll do a quick revision of this. Shortest path is actually super interesting. You can also use water to find the shortest path in a maze, or you can use electricity to find the shortest path in a maze. This has nothing to do now with this algorithms and data structures course. I just found these videos on YouTube, and they discuss other approaches than algorithms to find the shortest path in a maze. You can apply our algorithms from today also to a maze, because you would just need for each state in here define what are its successors, like north, east, south, or west. What's the start? What's the end? And surprisingly, you can even use water or electricity to find the shortest path in a maze. So these videos, they are not relevant for the exam in this course. I just find them quite interesting. It's one video actually about different approaches, about water and electricity. You may find this interesting as a video for the weekend. Next week, we will take this approach to another level with the lowest cost algorithm. And lowest cost is an extension of our shortest path. So our actual actions come with costs. So this could be that maybe going from one city to another costs 5, or pouring is more expensive than emptying or filling. And then with lowest cost, we don't look at the total number of actions, but actually the total number of costs, where the individual actions come with individual costs. In order for you to understand this extension, you definitely need to revise this algorithm from today, understand the pouring problem, maybe rewatch this recording, and try the pouring problem maybe in a debugger, and familiarize yourself again with function references, functions within functions, these data structures here, and probably rewatch this recording to fully understand, because I know it's tough, but we're now able to solve generic stage search problems, and we will rediscuss next week some of the advantages of that. Are there any questions right now? If you have a question, maybe send a thumbs up, then I'll wait for you to ask your question or send it to the chat. If you're okay, maybe just send a red sticker. I know you're okay then. And one person says, amazing. I know it took like half an hour longer, but I wanted to make sure that you can work next week on some more of the coursework. There's also one recommendation, how I built the successors function. There's something quite helpful in Python. It's the iter tools. And every year, some students, they struggle with these iter tools. And they say, oh, they don't know what it's useful for. You don't need the iter tools, the combinations with replacement. It's just a helper that I found super helpful when writing my successors function, but there are obviously lots of other ways how you can build your successor function. You don't need the iter tools. Yet, if you're curious about Python, maybe take a look at the iter tools. There are some super helpful functions that can help you with a huge variety of Python problems, and you wish such functions actually existed in other programming languages. So, since there are no more questions, we are done for today, and I wish you a great weekend and enjoy the revision. Spend enough time on the revision, and next week we'll continue with lowest cost. We will finish the crafts, and we will start looking into complexity theory next week as well, which will help us to analyze if algorithms are efficient or not. Take care. Bye-bye.